In this video, I'm going to introduce some important definitions that we're going to keep in mind throughout the course. The first concept is that of a domain. Now, a domain is a subset of the set of complex numbers that's open, and you can take any 2 points in that set and join them or connect them using broken line segments completely in that domain D. Now, what does all of this mumbo-jumbo mean? Well, here's a set D, and I've picked out 2 points in it, z sub 1 and z sub 2. And I can join z sub 2 to z sub 1 using this path of broken lines or zigzag path that's completely in the set D. So that's what makes D a domain. That is, you can take any 2 points in it and you can connect them using zigzag paths that lie completely in the set D. Now, what would be an example for a set that's not a domain? Well, let me draw something pretty weird looking. Let me draw this and this, and collectively call the subset of the complex plane as D. Now, is D a domain in this case? Well, if I take some point here, z sub 1, and some point z sub 2, there's no way to join them by means of any path lying completely in the set D. So this is not a domain. Other examples of sets that are domains are open half-planes. For example, if I take the complex plane and I consider 1/2 of it to be all the complex numbers with a positive real part, well, this would be a domain. And similarly, you can have open disks. Now, an open disk would obviously form a domain, and so would an open punctured disk. For example, if I take the complex plane and I just draw a disk here of some finite radius, but that disk has a hole in it, specifically it has a hole at the origin. So this is an example of a punctured disk. So I've just drawn this hole around the origin to emphasize that it's just not there. So even in this case, you can join any points within the disk using broken line segments or zigzag paths that lie completely within the disk. Another important concept is that of a convex set. Now, for the case of a convex set, you want to take any 2 points in that set, but join them using straight line segments contained within it. So the open half plane, yeah, this is a convex set. This open disk is definitely a convex set. But there's a problem with this open punctured disk. Because if you want to join 2 points, say z sub 1 and z sub 2 that are diametrically opposite, then the straight line joining them passes through the origin, which is not included in the set we're talking about. So no, this is not a convex set. Another important concept is that of a star-shaped set. Now, a set S is star-shaped with respect to some z naught belonging to S if any other z belonging to S can be joined to z naught by a straight line contained in S. A nice example of this, now remember, when we talk about star-shaped, we mean star-shaped with respect to some complex number in that set. So a nice example would be the slit plane. Now, what exactly is the slit plane? Well, it could be something like the set of complex numbers excluding the negative real axis and 0. So I've drawn this previously in a video on, I think, yeah, it was about that complex exponential function. Specifically, I'm talking about the rotation operator. So if you take the complex plane and you introduce this branch cut, you get the slit plane. That's the complex plane minus the negative real axis and 0. Now, this is in fact star-shaped with respect to any z being a real number. So if you take any point here on the positive real axis, you can join it to any other point in the slit plane by means of a straight line that lies completely within the slit plane. So it's star-shaped with respect to any z being a real number. However, if you pick something that's not on the real axis, for example, if you pick this point over here, then you can find this point over here, and if you join them by a straight line, you end up crossing something, you end up crossing a path that's not included in your set. So it's not star-shaped with respect to any point that's not on the positive real axis. And you can call a domain D star-shaped if D is star-shaped with respect to a z belonging to D. So if it's star-shaped with respect to any one of its points, it's called a star-shaped domain. Finally, I'd like to introduce you to the concept of a complex valued function. So if you have u and v as subsets of the set of complex numbers, you could define a mapping f that takes elements of u onto elements of v and write this as w equals f of z, where w is an element of uppercase v and z is an element of uppercase u. So this here is what we call a complex valued function. And complex valued functions may be single-valued or multi-valued. A very simple example of a single-valued complex function would be f of z equal to c, where c is just some fixed complex number. So this is the constant function, and this is single-valued. Another very simple function is the identity function, f of z equals z. That's another single-valued function, and I already introduced you to a multi-valued function. Remember the argument function, f of z equaled arg z. This here is a multi-valued function, and we discussed this when we constructed the rotation operator in the complex realm. And the cool functions in complex analysis are multi-valued functions. And a lot of times when we'll be constructing complex valued functions, we'll be dealing with how to make the multi-valued functions single-valued so we can define them continuously. And that's going to be lots of fun. But that is, of course, the subject of future videos. Right now, I'd like to dig a little deeper into the structure of a complex valued function. So if I say that w is a function of z, doesn't this mean that it's a function of the real and imaginary parts of z? And because w is just another complex number, so I can write this as a real part plus I times an imaginary part. So I'm writing lowercase u and v as the real and imaginary parts of this complex valued function f of z. Okay, cool. So basically I have f of z, or f of x and y, being equal to u plus I times v. So doesn't this mean that u and v are both functions of x and y? And we know that the real part u and the imaginary part v, both of these numbers are real numbers. So what we have here is just a couple of real valued functions of x and y. But wait a minute, isn't this just a throwback to multivariable calculus? So yeah, fire up that DeLorean. Multivariable calculus, or the knowledge of multivariable calculus, that is, comes in handy quite a bit while studying complex analysis. For example, if I say that the function f of z is continuous, what I'm trying to say is the real and imaginary parts of the function are continuous functions in the traditional sense of multivariable calculus, which is pretty cool. We're familiar with that. We studied that, and hopefully we all passed it with a good grade and decent understanding. or at least just a decent understanding. And I think that's enough for now. We'll be dealing with the calculus of complex value functions later, but first I want to construct all those functions. And in the next video, we're going to be constructing the exponential function in the complex realm. So I hope you enjoyed the video. I hope you learned something. Be sure to like and subscribe. Thank you. See you next time.